Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Alright, welcome back. For this problem, we are doing with an equation that I've never seen before, and that makes this all new and exciting, right? So, it has to do with the flow rate in a needle. So the flow rate Q, this right here, should say this at the very start. Flow rate, that's going to be a volume per unit time. So the dimensions are going to be, dimensions of volume are length cubed. So that's gives us our volume divided by time. That's going to be our flow rate. So the equation for it is pi r to the n, pressure 2 minus pressure 1. One of these pressures is the pressure, well, the pressure at each end of the needle. So we're finding a difference in needle pressure right here. I just went off the board. That is equal to mass per length times time squared. All right, this is all over 8. This is the Greek letter eta. It is viscosity, which is measured in mass per length time and divided by time, length, which obviously has units of length. All right, so that is a lot of stuff right there. We are going to rewrite this, substituting in all these dimensions. That'll make this look quite a bit nicer. Pi does not have any dimensions, so we're going to leave that out. R is the radius of the needle, so that has dimensions of length. So we got L. When we subtract two pressures from each other, find the difference in pressures. That's gonna result in a pressure. So don't worry too much about doing any subtraction right here. We're gonna just write what that comes out to be, which is gonna be something in terms of meters per length per time squared. The A is dimensionless. Eta has dimensions of mass per length times time. L has dimensions of L. All right, we can rewrite this right side a bit, make it prettier. This LT right here is gonna, if we divide something in the denominator by something else, then that kind of is the same thing as multiplying this whole fraction right here by it. So we can basically bump those up to the top. Kind of the opposite is true right here. If we're dividing mass times length times time squared, it doesn't matter if we do it up here or we say it's multiplied times the denominator of this fraction. So length times squared times mass times length. All right, and so we've got some canceling out we can do here. We cancel out the length right here, mass, and one of these times right here. We are left with, one of these was supposed to be a length to the nth power. I seem to have left that out because this r to the n right here, that's what we're trying to find, what this value of n should be. So L to the n over TL. Or rewrite this down here. So here's the left side of the equation again. The flow rate is equal to L to the n for time times length. So if we're trying to solve for n right here, we can multiply both sides by t. That'll make those cancel out because there will be a t here, The denominator and numerator cancel out. All right, we can multiply both sides by L. I'll write that over here. Multiplying both sides by L gives us L to the fourth is equal to L to the n. That means that n is going to be equal to 4. So if we just want to write out this flow equation again, with the proper value of n, it's going to look something like Q is equal to pi r to the fourth, pressure 2 minus pressure 1, all over 8 eta times the length of the needle. And there you have it. There's the magical number we were looking for in the problem.